and welcome to our third lesson in a series of our Newbie Diaries. In this lesson, we're going to talk about yet another pretty important and introductory topic in our language, data manipulation. The reason I think this topic is important is because when most people start using R, they mostly rely on its capability for statistical analysis. However, they're still very much dependent on more user-friendly applications like Excel or other spreadsheet applications for performing data manipulation. However, this dependence prevents many people from taking full advantage of our programming capabilities and learning the program more deeply. Here is a short plan for our today's lesson, so feel free to jump right into the parts which are most interesting for you. And we'll start right here. So to start, I'm going to install the package called Nutshell. This is a package which was created specifically for the book R in a Nutshell by O'Reilly Media. And many of the formulas and functions we're going to use in this lecture today are covered in this book, so I really recommend it. So I'm just going to write those 3 lines of code, and this is not something you need to know, so you just can copy it if you're going to use the same data. If not, you won't even need it. So I'm going to upload the library, and we're going to use the data which is called DO30. So this data frame or table contains data about 30 different stocks trading over the period of 252 days, and there is open price, close price, and a few other different metrics. So we're going to see it. So we're going to start by making sure that we are looking at the right data. Very often we try to import the data and we know how big it should be, meaning how many rows, how many columns it contains, if it's a table. But once we import, we don't see this data. So one way to see if you're looking at the right amount of data is to run this dim function, which stands for dimensions. And once we do it, we see that R prints out the dimensions of the data. So since we have a table which is essentially 2-dimensional data frame, and this table contains 7,482 rows and 8 columns, which is what I expect to see. Also, for a table, if we run command names, it will give us name of each column in a table. And an equivalent for table would be also to run function call names, so it will produce identical output here. And you may remember from last diaries that head function will just print out the first 6 rows of the data. So it's a pretty convenient way to visualize how your data looks like. So here we see that the first column contains symbol, then it's date, then it's open price, high price, low price, close price, the volume on that date, and then it's JSON close price. One additional useful thing may be to check what is the class of each variable. And we haven't talked about different classes of objects in R, but for the purpose of this class, you just really need to know that some variables are numeric and some variables are text. And by looking at the data, you cannot actually know whether number is interpreted by R as text or numeric. And this is something you may want to check because some functions work only if you have numeric variables. So by running class function on the entire table, we're going to get this class data frame, which is exactly what we're looking at. So we have a 2-dimensional data frame, which is table. However, if we run class function on some specific column, so here I just subset it to look at all rows in the third column, so it essentially selects the entire column and it's a third column. And by running this class function, I see that this is numeric column, so it's open price, which is good for us because this is exactly what we want to do. And here I wrote just a short loop which will do the same thing, but essentially for columns from 1 to 8. So once we run it, we actually going to see class of each column printed. So we see that the first 2 columns are factors, which is just to say that they're strings. And actually date here is also interpreted as string, but we can convert it to date, and we'll do it later. And the rest are numerics. So now, once we are sure that this is the right data we want to work with, we can move to our first operation, and the more simple one is actually to filter the data. Let's say we want to see all variables, but only for a specific stock. But we're not sure what stocks are here. So to check what stocks we have, we can run levels function, and we will run it. If you run this levels function on any factor, it will print out all levels or all different strings which are available in this column. So once I run it, we see that there are actually 30 different stocks, and let's try to filter out this table so we have only data for IBM stock. To make it a little bit more simple, I'm going to run this attach function, which will actually create in our workspace specific objects for each column, so we don't have to append table name before we call out each specific column. So I'm going to run this function, and now what I'm going to do is to create an object which I call do.do30.ibm, and to this object I'm assigning a subset essentially of our table, original table, but only rows where symbol, so symbol is a column, has value equal to IBM. And notice I have a comma here, so I'm specifying this filter before comma because I'm filtering rows, and I'm going to select all columns so there's nothing after comma. I have my object do30.ibm created, and then when I'm trying to print out first 6 rows of this data, I see that in symbol column we have only IBM stock, so that's what expected. We can also filter data based on numeric values. So let's say we'd love to look only at the 50% lowest close value, opening values in this table. So we can create another object, which I called here, just kind of extended to the same name, but dot lower 50. And I'm filtering our second table we've created, and I'm specifying here that so essentially I want the column open price, and notice that here actually I don't just say open, but I have to append the table name because this open object refers to the column in our first table, whereas I want to filter our second table. So I specify table name followed by $, and then column, and I'm saying that all values in this column should be less or equal to the median value in this column, and that's only these rows I want, and then I still want all columns. So once I run this command, we have object created, and when I print it out, we see that well, actually we can't really say because it's not sorted, but what happened here is we actually have only half of the initial table and the half which have lowest 50% of opening prices. We can check it by just actually running dim function and copying the table name here. So we should see that dimension of this table, it has 126 rows, whereas if we run dimension on this table without filtering by open price, it should be twice bigger, so it's exactly 252. Now let's jump to the next operation with sorting table by one or more columns. So one of the most intuitive ways and a little clear ways to do it is to create an indexed object first, and then apply this indexed object to kind of organize your table. To create an index object, we run this order function, and within its brackets we put the column for which we want to derive an order object. So it will, it's actually easy to just show what it does. So I'm going to create this object, and then I'm going to print out the first 6 values in this object. And we see it's 209, then it's 209, 208, 210, 203. So what this shows is that the first value in this table is actually not the smallest one, but it has 209th position if they were organized. And then the second has 208th position, and then the fourth one has 203rd position. Now we can use this order object actually just to kind of subset our table, but we will reorganize it and we'll produce a new object, the same table, but we'll just call it sorted. And in the rows index, we will input this index object. And since we want all columns to be sorted, I'm just going to put nothing after comma. And after I run this command and print our new table, we see that our close price is actually here increasing from the lowest value to the highest, to the next highest, and it's always increasing. So if we print all table, we just see it going from lowest to highest, and values in all columns were sorted based on the index of this column. We can also do it in the opposite way using the decreasing order. The only thing you have to change when you create index, you should specify additional parameter in your function, which is called decreasing, and set it to true because it's set to false by default. So we will create such index object, and then we will again create sorted table, another object, by running this, basically just creating a subset of our original table with a different order of values in all columns. So once we do it and run head function, we see that here we start with the highest close price, and then it goes down, 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 down. So that's basically how you sort values. You can sort based on any numeric values. You can also apply multiple conditions to sorting data. You can essentially create index for a few columns and then use it to sort the table. Next, we'll talk about adding new variables or transforming existing one. So I'll give you just like artificial use case. We have here opening price and close price, or high and low, and let's say we'd like to actually derive something average between our high and low, and so it's just taking high and low and dividing by 2. Now we can define very easily this new variable in the following way. So we specify table name and then followed by $, and then we come up with the name for this column. So in this case I just called av.price for average price, and then we use assignment operator and we specify the formula for this new variable. So since we're working now with this original table for which I ran the attach function, we don't have to say this refers to high in this table. It already knows it, so we just type high plus low divided by 2, and it will create this additional column in this table. So now once we run ahead on this first table, we see that it has now 9 columns, and the last one is this average price, which is indeed the price between high and low. So that's what we wanted. You can also transform variables. So let's say we have volume variable, which is represented here in units of stocks, and we may want to choose represented in thousands of stocks. So in order to do it, we just specify which column we want to transform, and we assign a new value for this column by specifying the transformation formula. So in this case, we just take original value and divide it by 1000. So after we run it, and then we try to see what are the values in this column, we see that they're actually converted. They're actually divided by 1000. So next we're gonna move to adding new observations. So we just added a new column, but let's say you want to add a new row to your table. Let's say you just had a new observation or you missed some and you want to add it to your data. So that's done actually very easily with simple assignment operator. And to exemplify it, I'm gonna here print out for you the last row of our IBM table. So that's just the one at the very bottom of the table. And now I actually here wrote a code which creates exact replica of this last row using this C function. So it just lists the values in this last row separated by commas, and the types of values are exactly in the same orders as they appear in the original table. That's something you have to make sure before you attach this last row. So I create this last row object, so when you print it out, we see that it has the same values as this last row of the table, but it kind of doesn't have those column names. But once we attach it to our table, which we do by just specifying a table name and then specifying an index. So here our table had 252 rows, so we say we want to put it in position 253, and it's not a problem that there's nothing there. We're actually going to put this object called last row, and it's going to fit there because we know it has 8 values. So now we're going to print the last 2 rows, row 253 and 252, and we see that indeed they are here and they're exactly the same, even though this first row was originally in the table and this last one I just inputted manually. This difference between index numbers here is just because this is indexed in the original table, the big one, and this is the index in the derived table. But if you work with the same table, it won't have this difference. So that's essentially how you can add new rows. Next, we'll talk about combining tables, and there are essentially two ways how you can combine tables. The first one is vertically, and the second one is horizontally. And the vertical way works that just you basically stack one table on top of the other, and this assumes that your tables have the same number of columns, and actually they have the same columns in the same order, if you want a date to make sense. So to illustrate this, I'm going to create another table for General Electric stock, which will contain all the data, but only for where symbol is equal to GE. And then I'm going to combine this, to stack it on top of the IBM table. And to do it, I'm going to run this rbind function, which stands for row bind. So we're just going to take those two tables, put them together, and produce a new object, which I called do30.ibm.ge. So, and we have an error here, which is probably because there is different number of columns in those two tables, and that's because we added a new column to the original data set, and then we derived the second table. So we should remove column number 9, and a very easy way to do it is just to type this table name and then say all rows column number 9, and we want to just assign value null, which means we just want to actually remove it. And now once we try to run it once again, hopefully we're successful. Now when we try to print it out, so we see that we are getting a new table which contains 505 rows and 8 columns. So it's the same number of columns as each of the tables had, and number of rows is just the sum of rows in those two tables. As you remember, I just added one extra to the IBM table. Now we'll talk about horizontal combination. So unlike vertical, when we stack tables on each other, horizontally we just kind of put them together side by side. And here the assumption is that two tables you're putting together have the same number of rows, and also they sorted in the right way. Otherwise you want to actually merge them, and that we'll talk just in a minute. So to illustrate this, I'm going to create one actually table or one column which will contain average price for General Electric stock. So for this reason I'm going to use this GE table, and since this table is not attached to the workspace, I'm actually going to specify table name and then column name. So it's high plus low in this table divided by 2, and once I run it, I have this new object. And then let's say I want to add this column to our original GE table, but I don't actually need the whole table. I just want the first 2 columns of this table, which is the symbol and the date. So I want symbol, date, and average price as I defined it here on this specific date. So this table is supposed to have only 3 columns. So also I want to rename this third column because I here called object average price.ge, just not to be confused, but once it will be in a table, it actually will be clear that this column refers only to GE stocks. So I'm going to just run this column names function and specify that I want to look only at third column here and assign to it the string average.price. So once I print this new table, we see that the first 6 rows and the first column is symbol, then it's date, and then it's average price on the date. So that's when you simply want to just kind of put two tables side by side, providing that the order of values in both tables makes sense. But sometimes you want to do merging. So merging in R is done with the help of the merge function, and it's equivalent to SQL join. And there are a few types of join, and you can implement all of them with the help of merge functions, specifying different parameters. The first and the most simple way is to use merge function by just specifying table names, and if both of your tables have a column which has the same name, and this column serves as unique identifier for all records, you just specify name of this column for in by argument, and the result you get is equivalent to the inner join. So we're going to run this command and just look at the dimensions of this new table and also how it looks like. So this new table has 252 rows and 10 columns. And the reason we have 10 columns is because the first table has 8 of them and the second has 3. But since we are joining by the date column, we kind of deduplicating this column from both tables. So we're getting rid of 1 and end up with 10. And the reason we have 252 rows is that because by running this function with these parameters, we are doing the inner join, so we're only bringing the rows which have values in columns in both tables. And you can also see that there is the symbol column which is present in both tables and has the same name, and in the resulting table it gets a new name. It's renamed by appending the name of the table to the original name of the column, so it symbol.x and symbol.y. It's essentially the same column, so you can remove one of them. So that's the inner join. To do the outer join, we use the same merge function, but we add additional argument all and set it to true. And to illustrate you how it works, I have another table here which contains date for IBM and GE, and the second table contains average prices for GE only. So by doing this, by joining those two tables, we will actually produce a new table which will have 505 rows, and that's because in case of outer join, we will include all rows which have match in either of those two tables, and the first one has 505 rows, so we're going to include all of them. And we'll also have, sorry, I should be looking at this line, we will also have 10 columns since we are joining by date column. If we wouldn't specify date here, R would actually be smart enough to understand that there are two columns which have the same name, and it would join by both of those columns. So the result will be a table with just 9 columns because it will deduplicate date and symbol from both tables. So to do the left outer join, we run the same command, but we specify not all equal to true, but we specify all x equal to true. So it means it should include all rows which are found in this first table. And from the right table, it will include rows only rows which have a match in this first table. And if they don't, it won't include them. So the result will actually be identical to the outer join, just because our second table has a match in the first table for every single record, but it wouldn't be the case, it would be different. And finally, our right join produces the table which has 9 columns and 252 rows. And that's because by doing the right outer join, from the first table we include only rows which have match in the second table, and all rows in the second table which has 252 rows. And finally, if both of your tables don't have a column which has the same name, or you set by parameter to null, the result you will get is going to be the full Cartesian product of both tables. So the dimensions of your table are going to be, the number of rows will be the product of number of rows in the first and second table, and the number of columns will be just the sum of them. Now we'll move next to the aggregating tables, and this lecture does not intend to give a full overview of how to make different summaries of data. It's more focused on the transformation, but some of the transformation actually allows you to do some useful summaries, so we're going to cover it here. To aggregate data, we use aggregate function, and just let me show you on this example. So what I want to see is all numerical variables summarized by the stock symbol. So I want to kind of get rid of the date and want to see the average open price, close price, high price, low price, etc. for each stock over all period of time. So to do this, I create this object with the name which I have selected, and then I run the aggregate function. And here the first parameter I'm specifying is the set of numeric values which I'm going to aggregate. And then the second parameter which should be necessarily list, even if it has only one column. And here I'm going to aggregate by the symbol. If we would love to aggregate by more than one, we could do that, but in this case it would actually produce our initial table. And then the function we want to apply. So in this case I want to apply mean, and also I want to remove missing values, so I specify this na.rm equals to true. And I'm going to run this comment, and also I want to show you how the result looks like. So I'm going to print out the first 6 rows of this new table, and what we see is we have a new column here which is called group 1, and this is exactly the grouping parameter which we specified here. So it has a symbol, stock symbol name here, and then we have all quantitative variables we've selected. So it's columns 3 to 8 in our original table, but it shows the mean value of each specific variable over the entire period of data we have here. So that's the aggregate function. Also, you can do contingency tables for categorical variables. So let's say you would love to see, or just to count, number of observations per stock per day, and I'm going to tell you the answer before I do it. It's going to be just 1, because there is only one record for each stock for each day. But if it wasn't the case, we could do just running the table function and saying, so I want to see the summary table of those two values, and what it does, it just creates kind of a cross table and put counts as values in the table. So here I've printed out the beginning of the table, and you see it's pretty huge by itself, and if it wasn't constrained by the space of the program interface, we would see a table which has this first 6 rows, and it would be super broad. It would have separate column for each date and separate row for each stock symbol. And then within the table we see the counts of values in our original table. A more simple case actually is to just run a table over one specific column, and what you're going to get is just the count of unique values here. So it's 252 values per each stock, and that's because each stock we look at the data over 252 days, and each day has a unique record. Next, we're going to talk about splitting tables by variable, and specifically by the categorical variable. So here's a simple use case we could have here. We have our data big table, and it contains 30 different stocks. And let's say we'd love to create separate table for each stock. We could definitely just do filtering and create different objects by filtering the initial table by different stocks. But a more simple way to do it would be actually to split our one table by this entire variable symbol. And for this we use the split function, and it will produce the object of type list. So I'm just gonna and this list object will contain separate elements, and each element in this list will be a specific table. So now if we want to see what is the class of the object in position number 1 in this list, we will see that it's actually a data frame. And if we want to print out this data frame, we see that, so we're getting the stock prices for only the first symbol here, 3M. And if we do it for the second element in the list, we would get another table like this. So we can actually access all these tables from this one list. Next, we're going to talk about cutting data into intervals. So as opposed to splitting, which works on tables or data frames, sometimes you may want to cut, let's say, numeric variable and turn it into categorical variable by cutting it across the whole continuum into a certain number of levels, usually equal. And you can do it with the cut function in the following way. So within the cut function, you specify numeric vector, and if it's not numeric, so you can use this as.numeric function within it to turn your vector to make sure that it's a really numeric. So here I'm applying it to the third column of our IBM table, and I'm going to split it into 10 equal brackets or 10 equal levels. So once I run this command and print the first 6 rows, I see how the data looks like. So we created new vector essentially, and each element of this vector contains the level. So there, in total, we see 10 different levels, but the vector will contain number of levels which is equal to the number of entries in the initial vector. So it assigns level to each observation in your numeric variable, and thus turning it into a categorical variable with only 10 levels. Now let's quickly talk about pasting values. So a very simple application. Imagine you have a column with name and column with surname, and you would like to produce a column which contains both name and surname. So to illustrate it, I just create simple vector of capitals and a vector of small letters. And when I run this command using paste function, specifying the first vector and the second vector, and then a separator which I would like to use. So in this case, I will use actually hyphen. So when I run this command and then print out the result, we see that what we have is the first element of the first vector, then separator, and the first element of second vector. And this forms the first entry, then there is a second entry, so on and so forth. So very simple function. Now let's talk about the transform function. Well, almost everything we've been doing we can call transformation, but there is actually a specific function called transform which allows to apply a few of the operations we've just done at the same time to the data frame. So here's an example. We run this transform function on our IBM table, and what we do here is first we turn date column into actual date format because initially it was specified just as text string, and then we also create new variable which we call meet, and we define it by the following formula. So it's open price plus close price divided by 2, so it's just the average of those two. And you see that here we don't have to specify that this meet variable will be part of this table because since it is within the same function, R understands it. Now let's run this and see the output. So just going to print the first 6 rows, and here we have our date. You don't see actually that it has changed, but if we print the class of this column, we see its date, and we see new variable, new column called meet, which contains the average of the open and close prices. So that's it for transformation. The ultimate thing we're going to talk today about is the reshape package. I haven't actually been using this package a lot, so you will be the one who will have to figure out the application, but I heard a lot of I heard a lot of very good reviews of this package, and people really recommended to know it, so I just wanted to show you how it works. To start, we're going to install this package and load it into the library. Oops. Actually, I have this package already installed, so I'm not going to run this code. That's what you'll need to do if you run it for the first time. And then we're going to use the data from this package called French fries. So I'm attaching this data, and here's how it looks like. So it has 9 different columns, all of which look numeric, and a certain number of rows. I actually don't know how many. And the reshape package contains 2 functions. The first one is melt, and the second one is cast. And you have to first melt your data, and then you can do casting part. So here's what melt function does. Imagine the following situation. So we have here our initial table with 9 columns, and once we run this melt function, we're going to say that on running this melt function, we're going to say that we want to preserve the first 4 columns of this table as they are, and the remaining columns we are just going to collapse into 2, where the first one will be name of the column variable, and the second column will be actually the value for the specific variable. So let's see how that will look like. So here's our new melted table. And as I said, there are 4 columns which look still the same, and then there's 5th column which contains number of the variable which were before placed each in separate column, and then the last column contains value for this variable. So potato 2.9, this comes exactly from here, then potato 14.0, this comes from here, and so on and so forth. So obviously this second table is going to be actually longer, since we collapsed a few columns and we had to add additional rows instead of them. Now you can apply the cast function to such newly melted table, and here's what the cast function will does. So we apply it to frenchfries.m table, and we say that we want to see the summary of all remaining columns summarized by treatment and representative column. So dot here stands for kind of, it's a standard way to specify all columns in a model which are not specified on the left hand side. So and we are going to apply the length function, which is equivalent to counting the observations per each category. So here's what the result looks like. We see that there are 3 different levels of treatment and 2 different levels of rep variable, and for each combination of those we see the number of observations in the table. This may look similar to the aggregate function, but I actually couldn't reproduce exactly the same result with the aggregate function. So you may want to try, but I think there is a certain value in this function as well. And the final topic for today is reshaping matrices. So the way matrix differs from a table by the fact that matrix contains the same type of values in all rows and all columns, whereas table can contain different columns, some of them numeric, some of them categorical. And to show how to work with matrices, I'm going to create a very simple matrix which will contain 2 rows and 4 columns. And then, well, one of the most frequent operations you may want to do with matrix is just transposing. So there is a special function. Very similar operation, however, done in a different way and which will produce different result, is changing the number of dimensions. So we have our initial matrix M, which had 2 rows and 4 columns, and we may actually flip number of dimensions and make this turn this matrix into 4-row 2-column matrix by running this this type of function. So dimensions of M and assigning it new value with the concatenate operator. So once we do it and print this new transformed matrix, we see that it has also 4 rows and 2 columns. However, it looks different from the transposed matrix because we see that transposition was done in a way that value in the first row and the first column was again in the first row and the first column, and then value in the second row and first column was placed in the first row, second column. When you change the dimensions, however, the transformation works differently. So you see that we have our values from the first column, and then it's again value from the first column, and then this is value from second column and again from the second column. So we kind of just go first by columns and by rows and pick up the next values to fill in new matrix again, first by columns and then by rows. And I guess that's it for this lesson. As usually, this code will be available on the tutorial webpage for you to practice, together with a cheat sheet to download and to revise functions we talked about today. And I encourage you to go to the discussion page, share your ideas, feedback, ask questions, and see you next time.